So I mentioned on Monday the idea of giving out the homework solutions at the same time as the homeworks, and I didn't get any comments on that. So I'm taking that as like this is that you're on board with the idea here. So I mean, I just want to stress, I want to make sure that everyone understands what the idea here is. The idea is, what I'm thinking is like you're working on a homework problem, you know, you're working on it as a problem, so you don't know that, you don't look at the answer before you do it. But then you sort of try and figure it out, you get something, and then it's like you want to know, well, am I done? And so at that point you can immediately look at the answer, and then if you got it right, then okay, you know you got it right. And if you didn't get it, if it's not right, then you can immediately go back and see where the flaw was. If you look at the answer too soon, you sort of lose the value of actually working through the problem yourself. And obviously, if you just like, if you don't try and understand the problem, then you get no value out of it at all. Yeah.
Can I just make a suggestion that
Yeah.
instead of like giving them out at the same time, there's
Yeah.
like some delay, like half week. So.
Sure, that's a good idea. So I could delay them, and I could certainly do that this week because I haven't issued them, and I don't actually know if I'm saying all this. I don't know if I don't know what the state of the solutions is at the moment. There's always normally a question of getting this, but that's a nice idea. The problem is that I think typically because I issue on Wednesday, I imagine a lot of people do them at the weekend. But you know, I want people to have them on hand when they do them, sort of thing. So that's the thing. But that's a nice idea. Yeah.
So you're thinking about forcing the answers or the entire work through the convolution?
Mainly the answers, not the entire work through. Yeah. Okay.
If you check the answer, if you're wrong, then you'll have.
But there's still a mystery. If it's not the right answer, it's like you don't necessarily know. Yeah. Okay. All right. Great. So we'll go ahead with that as soon as once I consult with Darwin and we figure out where the solutions are and what we can do. And I'm sorry we haven't got the first problem set graded yet. Again, it's taken us a little time to figure out the how we're going to do this. So, but hopefully we'll get them back to you soon. Okay, so let's move on. We were talking about discrete time systems, things we can do in the time domain, and in particular, we introduced this idea of convolution as the essential operation. It's what the kinds of systems we're talking about, the linear time invariant systems that are composed basically of delays and gains. That's what they do. They perform convolutions, which, you know, on the one hand seems like a relatively simple thing, but they can be quite complicated, like the sound of a reverberation in a room. And then because of the nice properties of convolution, it's commutativity and associativity, you know, that allows us to do some algebra with convolution, although not all the algebra we might imagine. We've sort of, you know, we've shown we've got this kind of operator here which looks a bit like multiplication, but it isn't multiplication. In particular, it's an operation on entire sequences rather than on single points. And so there was an interesting question that came up this week about, like, well, if I have an expression like this, and I replace n with n minus a, you know, what does that really mean? The convolution, obviously, if you have the h of n plus y of h of n minus a and plus y of n minus a, then it doesn't really change anything if you shift the time indices by the same amount. But if you delay the input and you delay the impulse response, then the convolution of those two signals is something very different. It's been doubly delayed. And so you have to think about what you're doing if you're just trying to blindly treat this as another operator, because it's an operator on sequences, not on individual points. When in doubt, the way to make sure that you're not messing it up is to write out the actual full convolution sum, right? This thing, that's well-behaved mathematical operators that we know about, and so you can't go wrong if you use that. Yeah, but this thing is safe for, you know, expanding over addition and for breaking things up into parens. But beyond that, you know, we're not making any guarantees. Okay, so now we've sort of got the idea of this, we can get into the more general mathematical problem that's actually being dealt with here, and that's this idea of linear constant coefficient difference equations, which are the discrete time analog of differential equations in continuous valued math. And it's sort of, I'm not, this part is kind of a bit mathematical and a bit weird to think about, and it's not very essential to what we're doing, except for a couple of things that come out, which are a couple of insights that come out, which is why it's worth going through it. So one of the insights is like the generalization of mathematics, which is that, well, so far we've been talking about x as an input and y as an output, and then a system as a way of taking an input sequence x of n and generating a new output sequence y of n, and then we can write down, you know, the expression. We can say y of n is equal to, you know, some function of x of n or some function of y of n for earlier values of n. But from the mathematical point of view, all we've got is two sequences, x of n and y of n, and a statement about their relationship, which in most cases will uniquely, it's either true for these sequences or not true. And so the general form of that relationship can be written in this very neutral way that doesn't have any preference between y and x as this difference equation. And it's just saying that we're going to take, so this is the sum for k equals 0 to n, d sub k times y of n minus k is equal to the sum from k equals 0 to m, p sub k x of n minus k. I could have used different summation variables on two sides because they're different things, but I didn't. And so all this is saying is, well, if you give me a sequence y of n, I've got a set of coefficients, and I'm going to sum up at a particular point n, I'm going to sum up some range of values of y around point n with these coefficients to get some value. And I've got the same kind of thing I can do on the left-hand side. I've got my sequence x. I'm going to take a set of points, you know, up to n plus 1 of these points, multiply them by a set of constant coefficients to get a value, and that for particular sequences that obey this relationship, those two values will be the same for all n. Right? So this is a statement which you can check. It's a statement about the relationship between two sequences, and it's either true or not. But this is our most general and neutral way of expressing these things. It's a difference equation. The difference equation is obviously defined, a particular difference equation is specified by these sets of constant coefficients, which includes knowing how many of them there are, the n and the m, and we call the larger of n and m the order of the difference equation, which is also the maximum number of history or maximum number of elements we need to store to calculate this thing. Now, as I say, this is obviously it's completely symmetric in x and y. The only thing that's not totally arbitrary about it is, well, it's got finite n and m, and they're always backwards looking, right? So it's always x of n minus k and y of n minus k. But of course, that's not really a limitation, because you could set some of these p's equal to 0 to have it be effectively looking forward. But it is finite order, so it's only looking over a finite chunk of x and y to express their similarity. But in this way, we can take the y for k equals 0, keep it on this side, and then move all the other values of y over to the other side, and we can rearrange it so that y of n is expressed in terms of y of n minus k for k greater than 0, and x of n minus k for k greater than or equal to 0. Right? And so this is the causal form, or the generating y as an output moving forward in time. That if I give you a certain sequence x, and then say that you can start at some particular point in time where you can assume something like the output is 0 up until that point, then we can work forward and calculate the next value of the output given these previous values of output and the ongoing values of the input. So this is the form we're used to, saying that y is derived from x, including maybe looking at previous values of y, which themselves were derived from x earlier, but it's just a more compact way of doing it. So this linear constant coefficient difference equation can be rearranged this way, but this is sort of saying, well, no, from the math point of view, it's not. I'm not saying that one's an input, one's an output. I'm just talking about the relationship between two sequences. Like I say, it's not really important to have an intuition about that, right? For me, this is the intuitive thing. This is the thing that I can build and I can use. And this is just like mathematically true. The point about this is that it's, it's the kind of thing that we can show to a mathematician. They can tell us interesting properties of systems that have that kind of behavior. Here, to get this yn over the side, we had to divide through by d0. But if we define that d0 as always 1, then there's a scaling ambiguity about this, right? If I scaled all my d's and all my p's by a certain factor, the relationship would still be true. So there's kind of one too many degrees of freedom here. If we just specify that d0 is always 1, then it's still the same set of expressions that we can write, and so that makes this thing a little easier to work with. That's normally we assume that we assume by convention that d0 is equal to 1. Okay, so if someone gives you an expression like this, a linear constant coefficient difference equation, and they say, oh, here's an x. If this thing works, we should be able to work out what the y is. If this is really a unique relationship between two sequences, we should be able to work out what the y is. So what we're going to do now is go through the kind of classic, closed form pencil and paper way of solving that. And like I say, this isn't that important from a practical point of view. But the point about going through this is it gives us an insight into the structure of the behavior of these kinds of systems. And so it's a little bit historical, but it's not pointless. So the classic way of solving these things is to say, well, if you give me an x of n and a difference equation, I can work out the y of n, and the way I'm going to work it out is by working out two different parts. Y sub c of n, the complementary solution, which is actually basically only depends on the left-hand side of that difference equation, only depends on the expression of y, and which is the coefficient, the decay coefficients. So the part over here that was the expression with x is assumed equal to 0. And then the particular solution, which is now the way that the particular x that came in influences it. And in a sense, this is about the linearity, the superposability of these systems, that if x were identically 0, right, if x of n was 0 for all n, then the right-hand side, the part that involves x, would be 0. This would be true. But it turns out there's still stuff that can happen on the left-hand side, on the output, even if the input has 0 state, 0, nothing. And then but then we can also solve for what happens when we do actually put the input that we have in, and we can add those two things together, and they'll still give us a valid solution to the whole system. So that's why we can break it down. But it's because of this curious behavior that things can happen to the system even with 0 input that we break it down this way. Now, of course, we've also said of a linear system that if if the input is x and the output is y, then if the input is alpha x, then the output's got to be alpha y. So if alpha is equal to 0, that is, if the input is 0 times x or 0, then the output's got to be 0 times y, also got to be 0. So wait, what's going on? We're saying that x of n is 0, but we're going to solve for what happens. Isn't what happens just 0? Well, it would be, except for this idea of initial conditions, that the input is 0, but there might be some other stuff that we're starting off with at our starting point, which is non-zero, and that's what gives us this complementary solution. Okay, so the idea about complementary solution is this idea of natural modes, that any kind of linear system like this actually has these states of oscillation, these states of vibration. And this is, this corresponds very closely to an intuitive thing that if you have something which is a dynamical system, it's got mass and springs and inertia, then if you hit it, which is like an impulse, then it rocks or shakes or vibrates or makes a noise. It doesn't just sit there rigidly and just deflect and then come straight back to nothing. And that's exactly what we're talking about here. The complementary solution is all about finding out what these natural modes are and then solving for their amplitudes. And it's kind of this really wonderful insight or very powerful law of these kinds of systems that when they're displaced, they will tend to oscillate with these complex exponentials, or in real terms, because the physical world is basically real, with damped sinusoids. Now there may be many damped sinusoids superimposed, but basically that's what you have. And so, I don't know if when you did differential equations, it was like, well, here's the differential equation, and guess what? The solution's always going to be e to the something. And it's like, don't ask me why, just let's assume it's true and it'll work out. It's kind of the same here. The solution's always going to be some exponential sequence here. And I don't have a good way to explain why that is, but if you assume that and just solve for it based on that, then you get the answer. But it is kind of this sort of observed physical truth that these systems have modes which are always decaying exponentials. Decaying exponentials in the case of real systems that are losing energy, although of course mathematically they could be diverging exponentials, which would be a system that is growing in energy with time. So to solve for the complementary solution, we assume that yc of n is something like lambda to the n, and then we said we're going to solve the complementary solution by taking the left-hand part of the difference equation, which was sum dk y of n minus k, and then taking the right-hand side and assuming it's 0. So this is that thing, but now we substitute in for y of n minus k, we substitute lambda to the n minus k. So we get this expression, which is now a polynomial in lambda.
So
Yeah.
the summation sign,
Yeah.
shouldn't k start from 1?
So shouldn't k start from 1? I'm taking this thing, right, where k starts from 0. We rearranged it here, but this is the thing we're going to solve, right? So we're starting k equals 0, and then we're just assuming this part we're ignoring this part, setting this part to 0. So this is the summation here. And so we end up with a finite range of powers of lambda with different coefficients, and we can divide out, the lambda to the n term, and we just get this finite order polynomial in lambda, where the order is n, the number of terms that are involved in the left-hand side of our difference equation, and the coefficients of the polynomial are simply the coefficients of the difference equation. And if we assume that d0 was 1, then the leading term is a 1. But again, you could scale it without loss of generality. So the solution to this is just the solution to this is some particular value for lambda, and the values for lambda come from this polynomial, this nth order polynomial in lambda. And we call it the characteristic polynomial, and it's determined just by the coefficients on the left-hand side of the difference equation. And of course, we know in general we can solve a polynomial like this by trying to factor it, trying to find the decomposition in terms of lambda minus a set of constants, and then if the whole thing's equal to 0, then it's satisfied when lambda is equal to any one of these values. They're the roots of the polynomial. And so we're saying that we can set yc equal to lambda to the n for any of these particular constant values of lambda, and this whole expression should be satisfied. That is, if we have if lambda is complex, then in general it can be one of these corkscrew things, these decaying things and if we take pairs of them that are conjugate, then we can add them together to make sinusoids. So we can have all these modes which are basically decaying sinusoids. And it turns out that they will satisfy this expression for all values of n, that if you just add together some little chunk of them with some coefficients, then these sinusoids are things that will have all those parts cancel out for any sort of part of the phase in the sinusoid, And so we get this, the complementary solution satisfied for all n. Because there are multiple roots here, it's not just lambda 1 to the n that'll satisfy it, but also lambda 2 to the n. So we're saying, which means that we can also add together lambda 1 to the n and lambda 2 to the n, it'll still work. And we can add together scaled versions of lambda 1 to the n, lambda 2 to the n, it'll still work. So we get, in general, we get n, big N roots to a polynomial like this. So we'll get big N terms here in our complementary solution with big N unknowns, that the scales, the amplitudes of each mode can be anything, and they'll still satisfy the complementary solution. And so we haven't really solved anything. All we've found is this, we haven't got an actual answer, but we've found a family of functions, all of which satisfy this condition that the x of n can be 0, these things can be y of n, and the whole thing is still solved. So in a sense, it's like, oh, the difference equation wasn't completely unique, right? Because there were bunches of different, this whole, infinite space of y sequences which I can put in, which are going to disappear because of the structure of the left-hand side. And so I can add these to any solution, and they should still work. But typically, we will have, in addition to the difference equation, we'll have some initial conditions. We'll say, oh, and at this particular time, here's some values, typically of the history of the system, the past conditions, saying, okay, you're starting at time n, but here's what it was leading up to time n. And then you can find the values of alpha that agree with this, and that's how you can resolve the ambiguity. If you don't have those initial conditions, then you can't get a single canonical answer because it's going to depend on those initial conditions. So that's how we get the alpha i's coming out of here. But right now, we don't have enough information. So again, the point about this is this insight that, oh, I've got this LCCDE system, this difference equation system, and it's got this intrinsic property, depending on the parameters of the left-hand side of the feedback part, the way the yn depends on y of n minus k. And what it is that there are these exponential modes which can be present in the system without any particular dependence on the input. That is great as long as this polynomial has distinct roots. There's a little bit of a twist if we've got repeated roots, so we can have a solution, we can have polynomial which factors like this with repeated roots. And that sort of isn't quite going to work in terms of the arguments I've made about degrees of freedom, because if I have alpha 1, lambda 1 to the n, and alpha 2, lambda 1 to the n, then alpha 1 and alpha 2 are not separate parameters. So we end up like, wait, we don't have enough degrees of freedom now. What happened? Well, what actually happens is that you end up with alpha 1, lambda 1 to the n, then alpha 2 times n, lambda 1 to the n. So lambda 1 does contribute to kind of distinct modes here, but one of them is just decaying away. One of them is growing with n. And this is kind of interesting, because what this is saying is if you've got repeated modes, then you can have this situation where the oscillation grows linearly with time. It doesn't make a lot of sense with these feedback modes, because like what would that mean? If I build a system with repeated modes, the energy is going to grow without bound. That's not really likely. Like if this was a very slowly decaying mode, then we're saying, well, the amplitude of it is growing linearly over time. But it does make a lot of sense when we see that we get the same kind of behavior if we're driving a system at a frequency which is also one of its modes, because then if you put in energy into a system and the energy is not decaying, then you expect the total energy in the system to grow linearly with time, and that's what this kind of n term means. But mathematically, if we have an order L repeated root, then we have up to n to the L minus 1, 0 through n to the L minus 1 as the sort of factors affecting these modes. This part is not very interesting to me, but we need to put it there for mathematical completeness. Okay, so these are lambda at the ends, which we can think of if lambda is real as like decaying exponentials, or if lambda was real and had magnitude larger than 1 as diverging exponentials. But of course, most of the interesting stuff is when lambdas are complex, which now mean that lambda I at the n is this kind of spiral thing, which is a complex exponential. And in particular, if we have a pair of them and they're counter-rotating complex exponentials, then when we add them together, the imaginary parts cancel and we're just left with a real sinusoid, which is something that we like. And so I just wanted to quickly show you a demo of this. I don't know how convincing this will be, because if I show you like, oh, I built this system and its output is a decaying sinusoid, it's like, yeah, I could do that. You just program a decaying sinusoid and that's what you get. But the point of this is that I built a system as a difference equation, and then what happened was I got a decaying sinusoid coming out. So this is pure data again. This sort of, and this is a, you know, a system for calculating signal processing, discrete time signal processing things that operates in real time at audio rates. So it means that we can actually hear it. What I've got here is just a general function generator that's generating. Is this actually working? Waveform multiply fine. That's not good. Okay, yeah. So this will play output. Why is that not prettier? This thing. Okay, hang on. Oh, here we go. So this thing is just a little function generator. I can generate sines or ramps or pulses or noise. And then it's going into this system, which I'll explain in a second, and then we're looking at the output here, which is the output of the system, which in this case, because I'm putting a sinusoid in, and it's a linear system, I'm getting a sinusoid of the same frequency but different amplitude out. Okay, so what's going on here is I'm using this particular operator in PD called fx, which is basically says, oh, you can write an arbitrary time domain expression here. So I'm saying it's the output here is y of -1 plus y of -2 plus x. And so that's just in our normal notation. It's saying the y of the current output, which is y of 0, is 1.99 times the previous output minus 0.995 times the output from 2 steps ago plus the input. And so this is just, you know, second order LCCDE with d with d1 equal to 1.99 or minus 1.99 and d2 equal to, there's a sign flip when you're taking the other side, and then p1 equal to 1. Okay, so it's I didn't put anything about sinusoids in here. I just told it to take the last two values, add them back, and feed them in, and then have it be driven by x. And what happens is if I put a pulse in like this, and now the input is just a little pulse train like this. If I bring the frequency down so we can see, you know, there are relatively few pulses. What we get out is this decaying exponential. Every time I put one of these pulses in, I have this nice sinusoid which decays away like this with an exponential envelope. You know, there's some aliasing in the rendition here, but take my word for it that if we'd zoomed in, which is not that easy to do here, we'd be able to see nice sinusoids decaying away. And then the next pulse comes along, we get the same thing. And this is actually exactly what the vocal tract looks like. When you speak, these little muscles flap together, they generate these transients in energy, and then the tube of your throat has resonances which cause ringing sinusoids like this. So it's like ringing in an electrical system, or in fact ringing in a mechanical system. So if I hit that, you sort of hear it rattling, and that's basically the same thing going on. So I don't know, that's just to say, yeah, this really happens. And then I guess while we're here, we should note that when we drive this with a sinusoid, at low frequencies we get a nice sinusoid out. As I move the frequency up, there's some frequency at which this sinusoid has a much larger amplitude than other frequencies. And that's when the frequency of the sinusoid matches this natural mode frequency. And then that's, I mean, you can sort of imagine you've got the system which is resonating a particular frequency, you're shaking at that frequency, and so it swings a lot. In a pendulum, it would be, you know, if you hit the pendulum, it swings backwards and forwards. If you shake the pendulum like this, it starts going further and further until it goes nonlinear, basically. So that's what we're talking about, and, you know, it's very easy to set these things up to demonstrate that. Any questions about that? Okay. So that was, you know, complementary solution, which is a little excursion into natural modes and natural oscillations of systems, of linear time invariant systems. To solve this whole difference equation, we said we're going to have to use the complementary solution, which we now know is going to be this set of modes with amplitudes yet to be determined, and the particular solution, which is the part that reflects the forcing function. So one way of thinking about this is, if you've got this these complementary solution, these modes, for a stable system anyway, they're going to, you know, if there's any change in the system, if you start it from some particular initial conditions, then the modes are going to be present, but for a stable system, which we'll define in a second, they're going to die away. And so at some point in the future, the modes will have decayed to zero, but if we're driving it with a constant input, say an input which is like a sinusoid, then it'll still be having the output at that point. So you can sort of think about saying, well, if I've got an input and I think about what's happening very late, very far in time, then it should tell me what's going on with the input. And in particular, if we buy this idea that these sinusoids or these complex exponentials are the eigenfunctions of these linear systems, if I can describe my input in terms of these complex exponentials, then the output should be the same complex exponentials, but just with some gain. And so all I have to do is solve for the gain, the scaling constant of the x of n, so that in general, if x of n is some exponential basis to the power of n, then I expect yp of n, the driven output at some large time, to be just beta times this same exponential basis, the same complex exponential, and then I just solve for beta by plugging it into the full difference equation. Of course, if lambda 0 is the same as one of my roots, one of my resonances, then we've got a situation where we're driving a resonance at its own frequency, and we've already got a term in this particular resonance in our complementary solution, one of the alphas, and then basically the beta is going to be the next available n to the L of that. So it's going to be, if lambda 0 is equal to lambda I, and lambda I occurs with, you know, is an nth order root of the actual system, then we'll get the next. That means it would have modes at, you know, lambda I to the n, n lambda I to the n, up to n to the L minus 1, lambda I to the n. And so we take the next one, which is n to the L, lambda I to the n. This is not the general case, although I guess it does. You'll probably see this. Certainly for large L, you're not going to see it, but maybe you'll see it for L equal 1. So I put it in there, but it's not really it's not intuitively all that useful, except for this idea of what happens when you drive a system at a resonant frequency. You get this buildup of energy, which is what that's sort of saying. Okay, so that's all we need to know about to solve this. So let's just go through it once to be able to do that. The idea here is that we now go through a solution, including going from the difference equation here to thinking about what's actually being described. So this is a difference equation, right? It's got some y's with some delays and some constants on the left-hand side. It's got some x's with some delays and some constants which happen all to be 0 apart from one of them. on the right-hand side. So this is the kind of thing we can solve. But of course, this is also a description of, this is a recipe for generating an output from an input, which we could draw as a block diagram here. And so I just want to draw that block diagram. What's it going to look like? Maybe I should do it on the board. Maybe that'd be easier. I'm trying to figure out how to do it in PowerPoint. What's it going to look like? So we have x of n, we have y of n. We appear to have a summation node drawn in here.
So you have a delay on the right side of this.
Thank you. Delay over here.
To the left, you have a scaling.
To the left, like this.
Yeah, and then another delay down.
Yeah.
And another scaling to the left. And then the first scalar is multiplied by the scalar. So now I have y of n equals
So,
we need another scalar of -1.
oh, interesting. Okay. So, what this is, that's great. Thank you. What this is saying is that y of n is equal to the output of this summation here. The summation here is x of n. This is, if we call this alpha, what should we call this? We should call this D1 and D2. This is, or something like that. Y of n is equal to x of n plus D1 y of n minus 1, right? It's got the delay in there, plus D2 of y of n minus 2. And then if we rearrange this to be in that form, it would be y of n is equal to x of n minus y of n minus 1 plus 6 y of n minus 2. So this should be minus 1, and this should be plus 6, right? But actually, I think I've messed up my d's. I think I should probably call this minus d1 minus d2. Then they would be the d's from the original difference equation, right? Because d1 is, d0 is 1, d1 is 1, d2 is minus 6. Okay, so imagine that I drew that in there. In order to figure out the actual values for this system in practice, we need to know what the input is going to be. So we're told the input is 8 mu of n, which means it's 8 for n greater than or equal to 0. And it means that it was 0 for n less than 0, but maybe we're not going to look there because we're also told some initial conditions. We're told that y of minus 1 was 1 and y of minus 2 is minus 1. And what that's saying really is we're going to build this system, but when you start running it, you have to have some values for the outputs of these memories here. And so saying, well, this one's going to, we call it y of minus 1, so it's 1. And we'll call this one y of minus 2, so it's minus 1. The implication is that at 2 points in the past, y took on those two, the last, up until the point that we're looking at, y took on these values, and then they sort of got pushed through this delay line. Don't look at that. But that's, it's not quite what we're saying. We're just saying, no, there are these two delay elements which have some initial value, and that's what they're going to be. That's how we define them. And we've got no other way of describing them. But in theory, we could have built this thing and sort of gone in there and written these values, and we've never actually had any previous values of output. It's just that's what we start off with in terms of in the state variable, state vector there. Which is something I'm going to, there's a reason I'm making that distinction. Okay, so we've figured out what this means, we've understood the problem, and we're provided with initial conditions. We need these initial conditions to solve it. In particular, we need as many initial conditions as we've got memory elements, because otherwise we couldn't build this and run it and get an output. But if we have all those values specified, then we could actually build this and just step it forward, and we could see what comes out. So we know that this problem is solvable, but now we'd like to solve it in a closed form way. Okay, so complementary solution. Here it is, just the left-hand side. of the difference equation set equal to 0. We assume that y of n is just lambda to the n. So we get the characteristic function here, lambda squared plus lambda minus 6. So lambda squared plus lambda minus 6 is equal to 0. And we can see that the solution to this is lambda plus 3 lambda minus 2, right? So 3 minus 2 gives us 1. 3 times minus 2 gives us minus 6. So those are the true solutions, which means the roots are the things that set these terms to 0. Lambda 1 equal minus 3, lambda 2 equal 2. These are roots which are real and larger than 1, so this system actually blows up, has divergent behavior, which is not normally what we deal with, but it allows us to deal with nice round numbers. So the combination solution YC of n is minus 3 to the n from lambda 1 plus 2 to the n from lambda 2, and then some scaling constants on each of these, which we don't know, which remain to be specified in order to make the whole thing fit to the initial conditions. The other part we need is the particular solution. The input is a constant, which we can think of lambda to the n for lambda equal to 1 times mu of n, but we're not looking at n less than 0, so that's not so important. So then we assume that the particular solution is also going to be a constant. It's like, beta times lambda to the n for lambda equal to 1. And then we plug it in. We plug in the particular solution here to the difference equation. And then in this case, because x and lambda don't depend on x and y don't depend on n, it just falls out, right? Because x is just 8 and y of n is just beta. So we get a solution for beta that comes out. But in general, we'd have, x was some lambda to the n, and then we'd assume that y was some lambda to the n. We could divide through by lambda to the n, and we'd still get just an expression that involved the constants. And we could cancel n out of this to get an expression, which would then give us the coefficient for the mode or the exponential that was in x that goes into y. And we could do that if x had several terms. We could do it for each of the terms, and we could solve for each of them. So now we've got this total solution, which is the two complementary solution modes with their scaling constants and the input frequency with a scaling constant. We don't know any of these scaling constants, so now we solve for them by plugging in the initial conditions. And in particular, so there are a bunch of different ways of doing this, and it's very easy to just have this be like a recipe that you do that you don't think about, doesn't have any meaning. It's just something that you go through. But for me, but then you might forget it and screw it up somehow. And so for me, the grounding of this, the way to remember what it is to think about this thing over here and say, well, I've actually got this. This is a real system that I could imagine working, and what I'm trying to calculate is what this output is here. And so I can do that just by, figuring out, by working through step by step what it's going to be. But my analysis has also given me this closed form solution for it, which is actually, the advantage of this is that I can calculate it for any value of n without having to calculate all the intermediate values, without having to run the machine step by step. But the math has guaranteed to me that these things are going to be the same. What I get by calculating the step by step is going to fit this. All I have to do is find the coefficients. So basically, I can just run this machine forward and then figure out the coefficients as I get values out. So I start off at time 0 because I got initial conditions for times -1 and -2, so I'm implicitly starting at 0. And if I write down the difference equation here, but for n equals 0, then I get y of n. This is the original difference equation, right? Y of n plus y of n minus 1 minus 6y of n minus 2 equals x of n. So I write down for n equals 0, and it references these two values in the past, which are my initial conditions. So I substitute in the initial conditions here, This one is not part of the initial condition, so here I use my algebraic solution up here. So I get y of 0 is equal to whatever y of minus 1 was, 1, minus 6 y of m minus 2, which is minus 1, so plus 6. Then x of 0 is 8. So here are the 1 and the 6 and the 8. And then here's my y0, which is alpha 1 minus 3 to the 0 plus alpha 2, 2 to the 0 plus beta. And so if I write this down for n equals 0, I get an expression in the alphas and beta and the constants. And so basically, how did I magically make beta disappear there? Have I already gotten beta? Yeah, beta is minus 2 because I can solve that already. So I know what beta is, so now I can also write this down. So now I get alpha 1, alpha 2, but I still haven't got enough information to distinguish alpha 1 and alpha 2. So then I have to look at n equal 1. I do the same thing. Now I've got y1, y0, and y minus 1. This is the initial condition. This was the one that we have at least an algebraic expression for from the previous step in terms of alpha. And then we get a new equation here. The y1 is alpha 1 minus 3 to the 1, alpha 2, 2 to the 1, beta still. And then here's my y of 0, alpha 1, alpha 2 plus beta, and my initial condition and my output. I get a second expression, alpha 1, alpha 2, and then I can solve for alpha 1 and alpha 2. So once I've solved for them, then I can just plug those into the closed form solution. So alpha 1 is minus 1.8 times minus 3 to the n, plus 4.8 times 2 to the n, minus 2, which was my beta that I solved for. And so what I've found is that given this set of coefficients, given these initial conditions, here is my output, which I can calculate instantaneously for any value of n. This point I don't really want to stress too much, but if you look at the examples in Mitra of doing this, he basically says, well, here's my closed form solution in terms of the alphas. Here are my initial conditions, y of minus 1, so therefore I can just write down that this expression must hold at that this expression, this thing must equal to my initial conditions at negative times. That works in almost all cases, except for a situation where you set up the initial conditions in such a way that they wouldn't be possible to arrive at from the input. It's sort of its unreachable state, and that can happen. And that's the difference between imagining that the initial conditions were something that happened in the past versus thinking of them as something that was just set up. You don't know how the system was set up. It could have been set up by some daemon going in and setting these state variables and just letting it run forward. The thing where you assume that you just set up state variables and let it run forward is guaranteed to work because it's this real physical thing that we're solving for. The other thing where you just assume that the closed form solution is valid for the times that the initial conditions describe is not guaranteed to work, but it does often work. But the thing is, like, I prefer my solution because I can explain what it's doing, whereas just saying, oh, it's just algebra and it just has to work is less satisfying, although I recognize that I've done a little bit of that as well. Okay, so that's not a big deal. That's why it hasn't been fixed in the 4th edition, but it's just like, I don't know, it's a little thing that niggles for me. Okay, so that's the example, and so yeah, okay, we sort of did what we were told to do, and we appear to have gotten a solution, which is good. Is it really the right solution? Of course, we can check it, right? So if we look in the MATLAB diary, I'm basically in MATLAB trying to work these things out. Now, to do it in MATLAB is a little bit clumsy because we're trying to access negative time values, but as we know, MATLAB wants to reference all vectors starting at time 1. So I have this convention here where I have my little time base here from minus 2 to 4, and then I'm defining this ZZ as kind of the offset of the 0 point within these MATLAB vectors. So I'm going to define these MATLAB vectors to be the values from minus 2 to 4. but then to get a particular point, I'm going to add the index that I want to ZZ, and then as long as I'm not going to indexes beyond -2, then when I try and set y of -2 here, I set the ZZ -2th point of the vector, which is which is y1, which MATLAB is okay with, so I can do this. And so this sort of allows me to write things down which look a little bit like what I've written in the in the math, but which MATLAB will still swallow. So here's that. I set up my two initial conditions here, which are basically the first 2 points of y. I set up my x to be 0 for the negative times and then 8 for all positive times. And then I just use a for loop to execute the machine. So I'm saying, well, I'm going to get y of n as x of n minus y of n minus 1 plus 6 of y of n minus 2, right? Which is exactly what we described over there with that thing. And I just do that for each n in turn. By the time I get to n, then y of n minus 1 has been set up in the previous step, and y of n minus 2 was set up 2 steps ago. And the whole thing just works. So if I, you can see what happened here, but if I just execute this in MATLAB, I just ran it, and I get a y. Whoa. Try that again. I get some values. Now, this is y of n minus 2, y of n minus 1. These are the initial conditions I set. But then these are the y of 0, 1, 2, etc. Okay, so and we could keep doing this for as long as we wanted. Instead of going to 4, we could go to 10. If I made x big enough, x equals 0. Let's make that super big. And then x of, what is it, zz to n, say, is equal to 8. And then I can do this. And now I've got y, but it's got the same initial values, but then it goes on. And because we have these divergent terms in here, it gets pretty big pretty fast. It's got, minus 3 to the n in there, so it's getting pretty big. But I didn't get these by using that closed form. I got these by just calculating the value and then feeding it back and accumulating it, right? So what we got from our solution was that we had these roots, lambda 1, lambda 2, and beta. And then we had these alpha 1s and alpha 2s, which just came from our analysis, from our solving the complementary solution and the particular solution. And then the contention is that the y that we get should be equal to alpha 1 times lambda 1 to the n plus alpha 2 times lambda 2 to the n plus beta. And so we can just calculate that in MATLAB. And then we're using nn as a set of n values that we're expressing. So we get a solution out like this. And n equals minus 2 to 4. And we get some values. And if we look at y of 1 to 7, they're the same values. Minus 1 and 1 were the initial conditions we set up, but then from time 0, 1, 13, 1, 85, minus 71, right? So these are numbers we got by calculating y of n by using previous values of y. These numbers we get by calculating this closed form expression for particular values of n, and we could have used any values in here. And lo and behold, they're the same thing. Okay, so that's just the skeptic's proof that yes, at least for this case, this piece of algebra analysis does indeed give us a way to calculate the outputs of a system like this without having to go through step by step, right? So I can set nn equal to 1,000, which I'll say 100. I can calculate yt as this nn. I get some number, and then I guess I could have done that with the for loop here. N equals 0 to 103, is it? Almost. What is y of end? So I guess if I make nn equal 99 and then calculate yt, it's close. Whoa, it's not that close. That's interesting. I don't know. They don't appear to be agreeing up at the 10 to the 47 level. This could be cumulated calculation errors. They should exist. So if I do it for 20, right? Just now I'm spooked. So y of zz plus 20 is that, and then yt. Yeah, so they agree up there. So when did they stop agreeing? 40. White, so nn equal 40. Okay, they're looking pretty good. 80, y of 80 and yt. Yeah, so they work out to 80. I don't know why it didn't work for 99. Okay, any questions about that? I hope you see what I'm doing, that I'm like, we're pulling together this thing that you can actually build and we can run step by step with this closed form solution. And again, the reason it's interesting is because, like, well, if I build this step by step, there's nothing obvious about this, is that the actual outputs I'm going to get are these sums of exponentials. But the analysis says, well, actually, yeah, you know, you're going to get something, and it's going to be highly structured. It's going to be the linear sum of a few complex exponentials for different exponential bases that we can figure out by looking at the complementary solution, the characteristic polynomial. Okay, so just to summarize, the difference equation is a set of constant coefficients for current and previous versions of x and y, and some initial conditions. We, by assuming that the right-hand side is 0, so left-hand side is 0, so we solve for the right-hand side equal to 0, assuming that y has this lambda form, we end up with this thing that will give us a solution, a polynomial in lambda, which gives us a set of roots, lambda I, and gives us this complementary solution, which is some scaling constants times those lambda i's as exponential sequences. We solve for the particular solution by looking at the exponential sequences that are the basis of x of n and solving for the eigenvalues of those, the amount that they're scaled by putting through this linear system. And then we solve for these unknown alphas and betas, or we solve for the betas just by looking at large, by solving for those eigenvalues. We solve for the alphas by plugging the whole thing in, the initial conditions at time 0, looking at the first few steps, basically running the machine, and then making sure that we do solve the alphas such that the output of the machine is equal to the results of the closed form solution. We had to solve that by looking at two different parts. There's a different way of breaking it into two parts that we could solve for independently and then add together to get the right solution. We can solve for the 0 input condition and the 0 state condition. The 0 input condition would be assuming that the input was 0 and then solving for initial condition, solving based on initial conditions. That would be basically solving for the alphas without beta, assuming beta is 0. We get some values for alpha, they'd be different values in this case. We then do a separate problem where we solved for the whole thing, but we assumed that the initial conditions were all 0. But we used the input, so we solved for x of n, and we'd end up with some alphas. But the idea is the alphas are only the ones that come from the transient, that come from the input. And then we could sum these two things up because these are both valid solutions to, a particular. This is a valid y for a particular x equal to 0. This is a valid y for a particular x equal to the actual x. So if we sum them up, we get something that still matches the difference equation. And because this had the initial conditions and this had 0 initial conditions, we can also superimpose those. And so these are both legitimate input-output pairs for the system. And because of linearity, we can add them together. This is not a desirable way of doing it because basically we have to solve the algebra for alphas twice. But the reason I mention this is because it's a more real thing. Here, when we did it before, we sort of had the solution which involved these unknowns, these alphas. Here, this is an explicit solution to an explicit problem where we solve the alphas and we get something out. And so is this. And so we can use superposition to add them together. But in a sense, the process we've talked about, the decomposition into complementary and particular solutions, is sort of like that, but just with a little bit of abstractness left in those solutions. What is the, if we know that the impulse response is a very important aspect of a system. Can define a system. We're now saying we can define these systems through LCCDEs. So what happens if we assume the input is a delta, and then we get the output of this LCCDE, the impulse response to the LCCDE. If x of n is a delta, then it's like, it's like some very large value times lambda to the n, where lambda is very small. So it's only finite for n equals 0 and then disappears, right? It's like infinity times 0 to the n or something like that. So the output is still so you can sort of think of delta as an extreme limiting case of a complex exponential, or at least for positive time. And so the particular solution is also some delta, some complex exponential. And we do the same thing of just plugging in, solving the difference equation. We have to find the alphas. It's going to be driven by the alphas, and we do this by looking at the initial conditions with this particular exponent. That we're going to have to find one beta. Here, this idea of looking at large n to find the beta isn't going to work because this thing is 0 except at n equals 0. But we can plug beta in at the, to this whole thing of stepping the machine forward, solving for our closed form solution to match the output of the system, and then we can still find these results. So here's an example of this. This is our same system, and we're going to try and calculate its impulse response now. And of course, when we're calculating the impulse response, we assume that the initial conditions are all 0. We're not allowed to say the impulse response when the initial conditions are not 0. The impulse response implies that we start off with 0 state. So we're basically solving the same problem, but now we don't have initial conditions, or the initial conditions are all 0, and then the input before was 8 mu of n. Now it's just 1. But because it's the same system, the complementary solution is still the same. It's still alpha 1 minus 3 to the n, alpha 2 to the n. The particular solution is now just beta delta to the n. So we plug in at n equals 0. N equals 0, we get the initial conditions showing up. That's set to 0. We get x of 0 showing up. That's set to 1. So we get alpha 1 plus alpha 2 plus beta equal 1. At n equal 1, we get these terms. N equal 2, now we need an extra expression because we've got 3 unknowns. We get, alpha 1 minus 3 to the squared plus alpha 2, 2 squared. And then, these earlier terms from back here. We get 3 expressions. We can solve for the unknowns. Turns out beta equals 0 here. There's no extra term, there's no extra offset at n equals 0. And we get the impulse response of this system by solving the LCCDE. And we could verify that in MATLAB by taking our little thing and plugging in a 1 and then just feeding back. And this is what would happen, that we get this divergence. Notice here that this is h of n. We're calculating it from time n equals 0 onwards. So this is only h of n for non-negative n. For n less than 0, h of n is 0. If we have this machine with 0 state, we put an impulse in, the output's going to be 0 before we put the impulse in. There's nothing going on there. And then at time 0, suddenly there's stuff and it decays away. So it's this expression, this closed form expression, is only valid for n equal to 0, or we could write this and multiply it by mu of n to make it implicitly equal to 0 for n less than 0. But the closed form expression has a limited domain that it works over. But it doesn't ever go to 0 for any positive n, right? It decays away, or in this case, it doesn't decay away. It diverges, but it has no natural end. And so even if these constants were smaller than 1, so it was decaying away, it would still have some non-zero value for every positive value of n. And so it would be an infinite impulse response. And in general, with any kind of feedback system, it makes sense that if you've got energy or amplitude running around like this, even if it's decaying away, it's never going to be completely cancelled. It's never going to be completely extinguished. And so these systems have infinite impulse responses. And it's the feedback that gives us that property. Before, when we looked at impulse responses, they've been feed forward and they had gone to zero. You know, the amplitude had fallen out of the bottom of the delay line, and so it had disappeared. But with feedback, it never fully disappears. Okay, there are a few things I want to get through quickly, just so that you have what you need to do the problem set this week. So this idea of stability is clearly important. In this case, when we look at the output of this system, if we in MATLAB, if we plot y, it's sort of, or stem it, say, it has some nice values and then suddenly gets very large. And if I stem 1 to 20, it looks like that. If I stem 1 to 40, it kind of looks like that again. There are more points, but the last few values are so large that the auto scaling makes these values look like 0. This is up to 10 to 17. So this system is not nice. The longer you let it going, the larger the values get. And if you tried to build this physically, at some point you'd hit the physical limits of what you were building. So we need to understand what's going on. And basically what we're saying is if we've got a system like this, where every step we double the output and then feed it back, clearly we're going to get an exponential divergence. This system, if we think about its characteristic polynomial, it has, the lambda is 2, and so that's why we see 2 to the n as the output coming out here. If we want to define stability, it turns out that there are the edge cases are kind of important. So we're going to use this particular definition of stability, bounded input, bounded output, or by both stability. And what that means is that a system is stable if for every possible input signal which has some finite bound on its amplitude for all values of n, then the output will also have a finite bound on its output for all values of n. And so basically it just says there can be no constant amplitude input which will lead to an unbounded growth of the output, which means we don't want any n times some constant amplitude terms in our output. In general, the idea is like, is it possible to make this thing get arbitrarily large without putting something arbitrarily large in? But it turns out that there are a few edge cases where you could have different definitions of stability, but this one is reasonably clear. And so if we have, just to show the examples here, our moving average filter, let's see if we can prove that this is bibostable. So here's the expression y of n is equal to sum of x of n minus k with 1 over m scaling constant. So the magnitude of y of m is equal to the magnitude of this thing by the triangle inequality, the magnitude of a sum of values. These values can in general be complex, say, but the magnitude of the sum is always got to be bounded by the sum of the magnitudes, right? It can't be any larger than if they're all positive and real. And so we can write that down. So, but we've got an expression for this, that the magnitude of x is always less than or equal to b of x for all possible n. So this thing has got to be less than or equal to n times b of x, which is clearly a constant value. So we can set some b of y, which is unconditionally larger than this, and we've got we've got a finite bound on our output. So we've got a bibostable system. If we had a system where where the modes were lambda to the n for some lambda with a magnitude larger than 1, then clearly we would not be able to write down a value of y that was a finite limit on how large it could get, because it would just get larger for larger n. Here we go. So we said that the LCCDE is always, the solutions always look something like this, some lambda to the n's. And so in order for them to be, typically for n larger than 0, we're starting at some particular time. We have initial conditions, and we're solving for the time after that. And so we need these lambdas to have magnitudes smaller than 1 to avoid them diverging, because the magnitude of this is always going to be the magnitude of lambda to the power of n. Okay, so just in the last 3 minutes, let me just talk quickly about correlation. Okay, I really hate doing this because like this is the obvious place to stop. But there's a question in the problem set about correlation. So let me just quickly run through what it is, and it's a very simple extension of convolution. The idea of correlation is it's about measuring similarity between sequences, and so if it's it's just an inner product. So the cross correlation of two sequences x and y is just over all the entire sequence x of n times y of n shifted, y of n minus l, so a shifted version of y. So it's just an inner product again, inner product of x and a shifted version of y as a function of the shift. And so it looks just like convolution, except in convolution it was x of n times x of k times h of n minus k. And so the summation variable was k. Here I'm calling it n, but x went in one sense and h went in the other sense. Here they're both running in the same sense, and we're just shifting them relative to each other, taking the inner product and working it out. And the idea there is that if they're very similar, if they're similar at some particular alignment, then you'll get a large inner product there, and the other shifts you won't get this big alignment. So it's a way of finding the particular shifts where two signals line up with each other. If we define it this way, then we can interchange x and y, and what we get if we rearrange this is actually if this is r x y, then r y x is almost the same, but the sign of L changes. So r y x of L is equal to r x y of negative L. And in fact, there's no really good convention of which is x and which is y. This is the one that's in the book, but sometimes it'll be different. MATLAB actually switched from one way to the other a few years ago. And it just means like, if the first argument, if you interchange the first argument and the second argument, you reverse the sequence. And so you have to make sure that you understand which order they're going in. So here's just the contrast. Correlation, x of k, y of k minus n. Convolution, x of k, y of n minus k. So it's the same if you flip the sequence y. So r x y of n is equal to x of n convolved with y of negative n, the time reversed version of y. And in fact, correlation is something that we're interested in because it's about finding matching patterns. And so you can build something that calculates correlation by building something that does convolution, i.e. an LTI system, but having its impulse response be the time reversed version of the thing you're looking for. And that's called a matched filter, where you build a system where its impulse response is constructed to be the negative of the pulse shape you're looking for. I'll show you an example of that in the next class. So finally, autocorrelation is just RXX. It's what you get if you do correlation of a signal against itself, and then because x and x can be interchanged, RXX of L must be equal to RXX of negative L, right? Because I swap them around. That's what happens when you swap them around, but you can't tell. So that means an autocorrelation has to be even, has to be symmetric around 0. RXX of 0 is x of n times x of n summed over all n, so it's got to be the sum of x squared, which is the energy of the sequence. And so the RXX is maxima at the middle. Okay, I think that's enough definition. Hopefully you'll be able to do the problem set. We'll talk a little bit more about correlation at the beginning of the next class. Any questions? All right, look out for the solutions to the problem sets. We'll publish them as soon as we can get ready, pick up them ready, hopefully by the weekend, and I'll see you on Monday.